Hello, and thank you very much for taking the time to click on this video. My name is Nicholas Kinsella. I'm a recent master's graduate from Ulster University in Northern Ireland. And during my master's thesis, I was very interested in detecting methane emissions. And I created a software tool called CH4 Sentinel, which works as an open source methane emission and measurement system that you can use on your laptop. So let's talk very briefly about methane. Why does methane matter? Well, methane is a very, very potent greenhouse gas. It's been estimated that around about a quarter of the total warming since the Industrial Revolution has been caused by methane. And it has an outsized effect on the climate. It has an impact that is 84 times greater than carbon dioxide over a 20-year period. Now, the curious thing about methane is that it actually doesn't persist in the atmosphere for very long. If you have 100 kilograms of methane that you release into the atmosphere, after just 12 years, only around about 35, 36 kilograms of that are going to be remaining. In spite of this, concentrations have increased since the Industrial Revolution 250% in the atmosphere. And just in my lifetime, I was born in 1985, concentrations have actually increased by 17%. So even in a relatively short period of time, the concentration of it in the atmosphere is going up and up and up. Now, as you can see from the pie chart, the largest contributor from human methane emissions comes from fossil fuels. And it doesn't have to be this way, because it's been estimated that between 50 and 80% of methane emissions from coal, oil, and gas can actually be completely mitigated using currently available technologies, and in many cases, actually at negative cost. Because of all these factors, organizations like the IPCC and the European Union have identified mitigating methane as the easiest win when it comes to dealing with the climate crisis. So how are methane emissions supposed to be handled? Well, first, the most straightforward way is flaring, which is what's happening in the video to your right. Probably not the safest way of doing it, but that's how he's chosen to do it. It's technically uncomplicated. Done correctly, it will convert 95% of the methane into CO2 and water. It looks terrible, but it does significantly reduce the greenhouse effect. Now, ideally, capturing and then selling that on the international gas market is actually the preferred option. The EU has something called the You Collect We Buy scheme, which is currently piloting in Algeria that aims to do just that. But the key takeaway point from all of this is that atmospheric venting is something that shouldn't happen. It's bad for the environment and it's bad for profits. Enter Hassan oil field. So this was the oil field that I chose to study for my master's thesis, and it's the largest oil field in North Africa. It produces around 36% of Algeria's national oil production. And when I examined it for the year 2021, I discovered that there were 5 methane super emitters that were producing methane on a regular basis. And in fact, 2 of them were very, very, very active. It's been suggested by the International Methane Emission Observatory that one of the emissions that I was studying actually went back as far as 1999. So these things have just been pumping methane into the atmosphere without flaring for a very, very long time. And it's just completely unnecessary. And as you can see, a couple of the graphics in the bottom part of the slide show a couple of the emissions that I detected. This is a screenshot from CH4 Sentinel where you can see an emission that has been detected and also an estimation of the actual emission rate. What does CH4 Sentinel do? It connects to free Sentinel-2 data via the Copernicus OpenEO API. It identifies and measures methane emissions. It gets you data 3 hours after capture every 2 to 3 days. And the detection threshold is 2 tons, which means that small detections than that will not show up in the system. It provides interactive maps that you can zoom in and scroll around so you can make rapid decisions, and it's fully open source with no licensing costs. So where does CH4 Sentinel fit in the broader methane detection field? There are many companies nowadays that actually operate methane detection systems. The market leaders are arguably GHGSat, and they have a constellation of satellites that are specifically tuned to find methane emissions. And they can get emissions as low as 42 kilograms per hour in ideal conditions. Now, where there is open source data that you don't have to pay for, Carbon Mapper is a great example of this. Often this comes with very, very slow data returns. So Carbon Mapper, although it will give you emissions that are as low as 100 kilograms per hour, you won't be able to access that data for free until a whole month after the emission has been captured. And so CH4 Sentinel is beneficial in that it can actually give you the information that you're looking for almost immediately. So how does it work? Well, the visualization is taken care of by using something called a multi-band, multi-pass approach, where band 11 and band 12 from Sentinel-2 are processed using the example that I've given you above there. And then what happens afterwards is a machine learning system kicks in. It uses the XGBoost regressive machine learning algorithm. And in most peer-reviewed studies that look at methane emissions, fairly computationally heavy physics-based methods are used to measure these things. But one of the disadvantages of using those methods is that you need normally like a core of CPUs to be able to run them. And when I tried to run it on my laptop, what I found was it just broke down. It couldn't handle just the amount of computational power required to actually do this. So what CH4 Sentinel does, it takes 70 plumes that have been captured using those heavy physics-based models, and then it uses that to train the system. Now, 30 emissions with known values were then used to evaluate this model, and it was discovered that the R² value was 0.81 and the root mean squared error was 1.34 tons per hour. Now, this actually compares very favorably to physics-based models using Sentinel-2 data because they often have uncertainties of between 14 and 67%. So CH4 Sentinel actually performs rather well. Now, how to use this? It's actually a fairly straightforward system. I've simplified it here somewhat. But all you have to do is simply choose a date that you would like to look for an emission when there is a Sentinel satellite passing overhead, of course. And then you choose a reference scene to compare that to. And that might be, for example, a scene that was the satellite passed previously, so 2 or 3 days before. And what you then have to do is you then look on the map, find your methane emissions, and then you click on them. And then you take the latitude and the longitude, and you place it into the plume coordinates box, and then you run the rest of the code, and then the system will spit out an estimate of the emission rate for that particular point source. Now, when you're looking at an area the size of an oil field, you often have to deal with something like this. So as you can see, there are lots of yellow features all over the map. Not all of these are going to be methane emissions. In fact, I know there are 2 methane emissions on this map here. There is, I don't know if you can see that, but my cursor is going over one in the bottom left-hand corner, and my cursor is going over another one. Where is it here? Somewhere out there are 2 in this scene, but trying to interpret this is somewhat complicated. So it's important to be able to recognize what is a methane emission and what is not a methane emission. So, and this is a problem with multispectral sensors like Sentinel-2, because they're general purpose satellites and they're not specifically tuned to methane, other gases are actually going to interfere with the signal. So as you can see in the graph in the top right-hand side, carbon dioxide and water vapor also actually intersect with band 11 and band 12 of Sentinel. Now, what this means is that if you have a very, very potent carbon dioxide plume or water vapor plume, that's going to look very similar to a methane emission. And so trying to understand what's happening at an oil field and how we can interpret which is which is very, very important. So I've created this little diagram to explain the differences. So in scenario A on the far left, where you see there's a plume visible in the true color image, but nothing in the shortwave infrared, that is not a methane emission. because methane obviously is invisible to the human eye and it is visible in the shortwave infrared. Now, looking at scenario B is what's called a diffraction spike. And it's visible in the shortwave infrared, but not really visible in the true color. What this is the action of burning off volatile gases in the oil field in the way we saw earlier. C is actually very, very similar to B, except that there is so much gas that's actually been burnt off there that we're actually seeing a cloud of what is likely a mixture of carbon dioxide and water, not methane. And D is what we're actually looking for. D is there's no diffraction spike. It's a very, very clear signal, and it doesn't appear in the true color, but it does appear in the shortwave infrared. So going back to Hassem Essaoud, based on the study that I did using CH4 Sentinel, super emitters have actually reduced their output by about 25,000 tons per year. I did a separate analysis by using something called the Integrated Methane Inversion Tool, which was developed by the University of Harvard's Atmospheric Modeling Group. That system gave a result of 29,352 tons per year as the total emission reduction for the entire field. And that indicates that around about 86% of total reduction came from these super emitters being turned off. And in the system itself, you actually can see these emissions being turned off because you have a graphic down here in the bottom left where you can see that I've actually been recording the actual amount, the values of each emission of one point source in particular. And then on the bottom right, you can see that there's actually a diffraction spike at the location where that emission took place. Now, that diffraction spike took place on the 17th of October 2024, and thereafter, no further emissions were actually detected. So this actually is a good example of actually where one of these emissions have been turned off. And incidentally, this emission, it's likely that this emission was going back as far as at least 2013 and possibly as far back as 1999, as indicated by the International Methane Emission Observatory from the UN. Now, if any of this is interesting to you, the full code and data used to actually make the system work is available on github.com/Nick Kinsella/CH4 Sentinel. You've got the full Jupyter notebook and all the data. I've also written a how-to guide, but not only for CH4 Sentinel, but also the integrated methane inversion tool that I mentioned earlier, because they complement each other really, really well. And also the research paper that deals with all the technical and scientific questions that you could possibly have around the system and how it works, as well as the specific setup for the XGBoost regressor, and as well as any other questions that you might possibly have. These are some references, and yeah, I hope you found that interesting. If anybody has any questions about anything I've said here, please feel free to reach out. I'm on LinkedIn, and I'm going to put this on YouTube, but I do try to look at the messages, and if I do see a message, I will almost always try to respond to it. So anyway, thank you very much. I hope you found that interesting, and take care.